I'm Bob Hedden, so I'm with Iron Oxide Recovery and Hedden Environmental, and I am the technical person on this project. I've been working with Amy Wolf and the Trout Unlimited Eastern Abandoned Mine Program for about a decade now, at least a decade, and this is a neat new project we've been working on lately. So I'm going to turn it over to Amy.
Great, thank you for joining us for this webinar. And as Bob had said, if you have any issues with hearing us or with seeing anything, at this point, just write in the chat box and we should be able to see it, and then we can address that. So we'll begin, and as Bob said, I am with National Trout Unlimited. I direct their Eastern Abandoned Mine Program and their Pennsylvania Cold Water Habitat Restoration Program. And just a quick overview of Trout Unlimited in Pennsylvania. Trout Unlimited works to conserve, protect, and restore North America's cold water fisheries and their watersheds. And we do that by protecting, reconnecting, restoring habitats in cold water watersheds and sustaining our work by engaging our future generations. And particularly in Pennsylvania, we have a large focus on abandoned mine drainage. We work with a lot of volunteer nonprofit organizations, conservation districts, and state agencies through our Abandoned Mine Drainage Technical Assistance Program. We're also engaged in a lot of on-the-ground A&D remediation. And we also do a lot of work for eastern brook trout cold water habitat with design and permitting assistance for bank stabilization, fish habitat projects, riparian reforestation, culvert replacement and inventories, and so forth. But moving forward to the focus for this webinar, let's just review some of, or two of our top pollution sources to Pennsylvania's waterways. And so we have abandoned mine drainage and we have agriculture. And on any given year, both abandoned mine drainage and agriculture in terms of sediment and nutrient pollution are both very large sources of impairments to Pennsylvania waterways. Each of these sources impair around or just over 5,500 miles of Pennsylvania waterways. So that's a combined impaired mileage of well over 11,000 miles of our streams. And so Trout Unlimited's interest in this is both cleaning up abandoned mine drainage as well as reducing nutrient and sediment pollution to our waterways. And the focus of this project is phosphorus pollution. And so getting right down to the nitty-gritty of this, phosphorus pollution is a major source of impairment to our waterways, especially as it is found in both dairy and swine manure. Both dairy and swine manure contain high levels of phosphorus. And particularly in the Chesapeake Bay, we have an issue where we have a lot of manure to deal with, but yet very little area to spread the manure, to dispose of the manure. Animal manure often gets applied at higher rates than the plant uptake. And so we'll be focusing on a portion of phosphorus that is water extractable, which means it is soluble. And we call that water extractable phosphorus, or WEP is the acronym, and we'll be referring to WEP, water extractable phosphorus, for the rest of this presentation. And that is the type of phosphorus that is environmentally mobile and that results in pollution in our waterways, and that is a source of impairment to aquatic life in our streams and ultimately the Chesapeake Bay and many other streams outside of the Chesapeake Bay. So overall, the agricultural-based phosphorus, or water extractable phosphorus, that is a significant contributor to water quality degradation in the Chesapeake Bay and other watersheds. Now let's go over to abandoned mine drainage. Now, as abandoned mine drainage is treated, and it can be through various methods such as active and passive treatment methodology, but we won't go into detail to that today. Something forms as a result of the abandoned mine drainage treatment, or the solids that precipitate out from mine drainage, and we refer to that as mine drainage residuals, or MDR as the acronym. So MDR, simply the solids that is produced through the treatment of mine drainage, and sometimes MDR is actually produced just as a result of aeration of mine drainage. And so MDR contains iron, aluminum, and calcium oxides, hydroxides, and carbonates. MDR is considered non-hazardous by the Pennsylvania DEP, and across the state, there are thousands of tons of MDR that are produced on an annual basis at treatment systems that are operated by active mining companies, the Pennsylvania DEP, many nonprofits, conservation districts, and so forth. So we have a lot of material for MDR. What is done with MDR? Well, up until now, routinely it's disposed of through burial or through landfilling. And actually managing MDR can be a substantial cost to the entities that are responsible for the operation of these mine drainage treatment systems. So before I go on, I just wanted to mention that, so we have a problem with agriculture, high phosphorus impairing our streams. We have a problem with abandoned mine drainage across the state impairing our streams. And Trout Unlimited sees that using mine drainage residuals to help or to control the phosphorus pollution problem is a win-win for our two top sources of pollution to Pennsylvania waterways. So how do these two connect? Well, MDR, which consists of iron, aluminum, and calcium solids, they actually have a capacity for absorbing or reacting with phosphate. And those reactions actually will shift the phosphorus to a solid form that is not water extractable. So shifting that to a form that is not water extractable phosphorus, that is what we want. And basically adding the MDR with the phosphorus absorption capacity should decrease the water extractable phosphorus and therefore decrease the environmental mobility of phosphorus. We're looking at MDR as a novel means to lower the P-source coefficient. We'll talk about that a little bit later. And also, there are very limited resources for folks who have to deal with high phosphorus concerns. So we see the use of mine drainage residuals as a means or as a new tool in the best management practice toolbox, if you will, for dealing with high phosphorus pollution. And again, it's a win-win for dealing with both the AMD problem across Pennsylvania and with ag pollution. So this project, which started back in 2007, we looked at a few questions. Do MDRs have chemical components of concern for use in agriculture? It's a new material, so we have to look at potential concerns with applying it, mixing it with animal manure and spreading it on the fields. Also, how effective are the MDRs for decreasing the water extractable phosphorus in manures? Do the MDR additions affect the crop yields? And how would MDR be incorporated into manure management practices, into nutrient management plans for agricultural producers? And so again, the initial grant was awarded in 2007. We started working on this project in 2008, continues through the present time. Trout Unlimited has been managing the grants in the project, with the principal investigator being Iron Oxide and Hedden Environmental, owned by Dr. Bob Hedden, who's here with us today. Funding for these projects, there have been several phases of this project, and it has come from first phase 1 NRCS, their Conservation Innovation Grant Program, which at the time was managed by the National Fish and Wildlife Foundation, and then phase 2 and 3 through grants from the Pennsylvania Growing Greener Program through the DEP. Our technical steering committee over these years has been comprised of some of the best as far as ag work goes here in Pennsylvania, and we have Doug Goodlander from the DEP, Office of Water Resources Planning. We have Pete Kleinman, Ray Bryant, and Clinton Church from the USDA Agricultural Research Service based at Penn State, in State College. We also have Dr. Rick Stihauer from Penn State University, Department of Ecosystem Science and Management, and also Phil Sabrell with the USGS, the Leaftown Science Center. And at this point, I'm going to turn the webinar over to Bob Hedden to go over some of the details of our project to date.
Okay, thanks, Amy. Okay, so first thing I'm going to talk about here is the MDR testing, and what that involved was characterizing the mine drainage residuals, the solids that we collected from 21 mine drainage treatment systems. We actually selected those treatment systems to range in the chemistry of the influent mine drainage and to vary in the chemical treatment technology used there. The treatment technologies range from no treatment, where iron and aluminum oxides just precipitated naturally from the water, to passive treatment, where there was limestone and or aeration, passive aeration used, all the way up to full-scale lime systems, which are operated by private companies or the DEP. We collected solid samples, and then we analyzed them. We measured the pH, we measured their elemental composition. We did that using ACT Labs, Activation Laboratories in Canada. They have a very good program for measuring a lot of the periodic table on solids. And we also measured the neutralization potential of the solids we collected using GNC laboratories in Brookville. And neutralization potential gives a measure of the calcium carbonate equivalency, because we always got, we often had questions from farmers if these materials could be lime equivalents, what the lime equivalency is. So that's what the neutralization potential provides us with. We then did testing. We did dose effect testing, where we would take a measured amount of MDR and we would add it to a known amount of manure, and we would measure the effect of that dose on the water extractable phosphorus, the WEP. And so a test would involve running a series of doses: 0, a control, 1 gram per liter, 2 grams per liter, 4 grams per liter, 8 grams per liter, 16, up to some number. And we did a few replicates within there, but our main goal was to hit a large range in dosing, and then measure the effect on the water extractable phosphorus. All the phosphorus measurements were made at the Penn State by the Agricultural Analytical Services Laboratory at Penn State. We also had Dr. Stihauer did a greenhouse crop evaluation study we'll talk about here at Penn State, looking at whether MDRs interfered with crop growth in a laboratory experiment. And we then have taken, just in the last 2 years, we've taken the MDR idea out into the field for farmers to test with us. So this is actually what we're seeing here. Here's a picture of some of our sites. The site on the right there on the top, that's called the Hughes borehole, and that is a natural deposition of iron and aluminum solids that occurs in Cambria County. The site beside it is below it is a lime treatment plant that's in Westmoreland County, and that's the aeration spot where the water is being aerated, lime has been added, and solids, as you can see, are forming. And the slide on the bottom is a passive treatment system, the Marchand treatment system, that's located in Westmoreland County, and that is a very large passive system that precipitates and produces lots of iron oxides that need to be managed. So the chemical variation, we ranged in our choice of sites from low pH, pH less than 3, where those waters tend to be polluted with iron, aluminum, and manganese, to neutral pH waters like the Marchand site at the bottom right here, which is neutral water, but with about 70 milligrams per liter iron, very serious amount of iron and a high flow rate. We looked at 5 treatment technologies: hydrated lime, pebble lime. Those are just 2 different types of lime that are used in treatment, and the choice of hydrated lime is the most mechanically intensive way to use lime in treatment, but it's the most efficient use of lime. Pebble lime is a form of lime that can be added directly to lime and can be used at more remote sites. Hydrogen peroxide is a treatment method for iron contaminated mine water that's gained a lot of interest and use lately. And we looked at one hydrogen peroxide site, and then in passive systems we had a couple sites where limestone is used to neutralize acidity, and then we have just standard passive treatment where aerobic systems like at the bottom slide here. In looking at the chemistry of the MDRs, we were looking for, from two perspectives. One perspective was just what do they consist of, and see what kind of correlations we could find between their chemical composition and their ability to react with and remove water extractable phosphorus from manure. The other aspect of our sampling was to determine whether these materials could be hazardous. And certainly that's a serious concern we've had from the beginning. We're taking waste products from mine drainage treatment systems and we're proposing to apply them to a food supply, a part of our food supply. And so clearly we have to be very concerned and careful about these materials. And even though the DEP doesn't consider them to be hazardous and they're allowed to be disposed of as in a non-hazardous manner, we thought we had to go to a higher level. And so what we went to, we talked to DEP and EPA, and the common response we got from those parties was that we should look at whether these materials would pass the EPA Part 503 biosolids rule, screening and the screening procedure. And these are rules that were set up really to regulate the addition of sewage, processed sewage sludge on farmland. And sewage sludge, if it's from a wastewater treatment plant, shouldn't have high metals, but sometimes some industrial waters could get in there. And so that was a concern. So the EPA and the EPA in particular came up with limits on biosol for metals in biosolids that are applied to land. And we used that as a basis here. Now we didn't measure the metal content of the manure MDR mixtures. We actually measured the MDR themselves. And because there actually is a very large solution when you add the MDR to the manure, this is a very, very conservative approach, a 99-to-1 dilution conservative factor here. What we found is that for of the 21 MDRs we looked at, we found that there were 2 that had an issue with nickel, and by issue we mean that exceeded the 503 biosolids rule standards, and one was a passive site and one was a lime treatment site, so there wasn't a correlation there or obvious association there. Arsenic was present in concentrations that exceeded the 503 rules in 7 sites. So arsenic is the most common metal of concern in these materials, and actually that's actually not surprising because iron oxides are very good, well-known sorbents of arsenic. And so actually what's probably happening is any arsenic that is in the groundwater systems is being absorbed by the iron oxide solids that are forming in these treatment systems, and it's providing a benefit to receiving streams, but not a benefit to using those solids. So what we decided in the project early on with the advice of our steering committee was to not use any of the MDRs that had elevated arsenic concentrations. But so what this pointed out to us that before any solid material is going to be used in a application like this, it has to be thoroughly characterized for its metal content. And while most of the materials that we looked at passed the 503 biosolids screening criteria easily, there are ones that don't, and so that needs to be taken consideration. Okay, the dose effect testing that we did, I described earlier that the way this was done was we took a measured amount of dried MDR from a particular site and we added it to a measured amount of manure, and we then, after a mixing the material on a shaker and then taking it to the lab, within about 48 hours, the phosphorus content, the water extractable phosphorus content was measured by the Penn State lab, and there we got our results. And we're going to show you what kind of results we got in the relationship between the dose and the MDR. One thing that came up as we were doing our experiments is we had to decide how we processed the MDR before we added it to the manure. And the obvious processing thing was the particle size. Many of these MDR materials, especially if they have a significant calcite or lime component, they're hard, and they're very hard materials, which if you don't crush them, that they end up being sand-sized or larger materials. And so we recognize that particle size might be important, because particle size impacts reactivity and particularly sorption. And so we did some experiments we're going to show you with, where we actually decreased particle size to see the effect on MDR reactivity. And I think that's where we are there. Okay, so then we'll go into actually some results. So we're going to see a few slides like this, and the slides are common in that the y-axis is the water extractable phosphorus concentration, and water extractable phosphorus is expressed it's the amount of phosphorus that was extracted by a water addition to a manure related to the solids content of the manure. And this measurement was developed by USDA and with the Penn State Laboratories assistance in trying to determine what is the best way to measure environmentally mobile phosphorus in manure. And this is the method they came up with, the WEP method. So that's the method that we used. And then on the x-axis here, what you see is the dosage, and that's grams per liter, grams of dry material per liter of manure. And I want to first focus on the solid symbols, which shows the effect of particle size on MDR on the WEP content. And so if we just go through, I'm just going to go through this one right here, the middle one. This is the medium particle size. Just to explain what we're doing here, this is where we added approximately 5 grams per liter of MDR to the manure, and the 5 gram per liter addition decreased the control, the zero, from about 3,300 milligrams per kilogram down to about 3,000. And then at 10 grams per liter, it decreased it further down to about 2,200. At 15 grams per liter, it decreased it down to about 2,000. And at about 20 grams per liter, it decreased it down to around 1,500. And so that's the way these experiments were done, again, increasing dose and effect on WEP. And what you see here for this material, and this material became our standard material. This is from the Brandy Camp lime treatment plant that DEP operates in the Toby Creek watershed. And this material, through work that's been done by Phil Cybrell, USGS, has been identified as a fairly good material for sorbing phosphorus from all kinds of waters, and from manure. So we were able to obtain about 50 tons of this material from the plant, and we processed it. And the early testing was to look at how decreasing the size of that material affected the reactivity. And what you can see here is that the coarse material, which is very gritty, sand or larger aggregates, had very little effect on the MDR. That's the top line. But as we go down through the medium and through our fine grind, which is the filled in triangles, you can see that we get much more effect. And we actually get the kind of effect we were hoping to find that we see for many of the MDRs. The other two lines then show you the actual results with this material. Let me go back a step. After we had determined that the fineness was very important, the particle size was important, we took those 50 tons of Brandy Camp material that we had prepared, and we ran it through a Pulva ball mill. And the Pulva ball mill then produced a very fine material, finer than our fine grade, with a mean particle size of about 20 microns. And that powder then was what we used in our field experiments. And what you can see here in the red line and in the open circles, the red open triangles, open diamonds, and the green open circles is the results of testing at the Evergreen Farm and the Sweetbriar Farm. And what you see here is that we see a similar result. We see as we add MDR to the manure, we decrease the WEP. we actually are seeing a greater result than we see in our field, in our laboratory studies, and that could be due to differences in the chemistry of the manure in a field environment as opposed to our buckets we collect from a farm at Penn State. Or it could also be because the pulva material was ground so much smaller, we're just getting more reactivity from it than we're getting from our hand ground fine material. So this is a very positive result. These results show that this idea has merit and it is effective. The other thing I want to point out here is the importance that we learned as this project went on of the manure, that the manure varies in its WEP content. And this was a surprise to us. And I think actually the USDA folks that we're working with, they're actually going to be exploring the variability of phosphorus contents of dairy manures and all manures in the future here, because what you see here is that the controls, the dairy manure that we collected from farms, this is untreated manure, ranged the WEP content from about 2,200 milligrams per kilogram up to as high as 4,800 milligrams per kilogram. And in fact, the 2,200 milligrams per kilogram manure doesn't have a phosphorus problem. That may seem like a big number, but actually in the phosphorus world, that is actually not an environmentally significant amount of phosphorus that is vulnerable to leaching out in large quantities to receiving streams. Whereas the 4,700 milligrams per kilogram is a big number and would be a concern on any site where that was applied. And so this was a surprise to us, and so we actually took that finely ground brandy camp material and we used it to treat 3 different manures. And these are all dairy manures, but one is a dairy manure with high WEP, and then the other 2 have much lower WEP. And what you can see here is that we eventually end out at large dosing rates at the same end result, the same WEP content. In this case, about 1,500 milligrams per kilogram. But the real benefit of the MDR approach for treating manure is going to be for the high WEP manures, not for manures that don't have a phosphorus problem. And that should be common sense. That seems like common sense now in hindsight, but since not all manure has a phosphorus problem, this approach is only applicable to those manures with a phosphorus problem. It's of interest, just the USDA folks who've been working with us, they became interested in, well, what is this WEP that's not being affected by the MDRs? And the feeling is that this is probably some organically bound phosphorus that just doesn't interact with the inorganic iron oxides and aluminum oxides and calcium oxides that we're adding with the MDR. So whether the manure chemistry is very important and whether this is a useful method for managing nutrients. Well, this is a slide that shows all the results of our field trials. And so when you look at again, the same thing, addition rate on the x-axis and the WP on the y-axis, and the 0 is all the controls. Whenever we would do a field trial, we would of course go out, and before we opened a bag of MDR, we would sample the manure that we were going to treat and get a 0 gram per liter addition rate. And so here you can see here the variability in the WEP in our 4 farm sites, ranging from 5,500 milligrams per liter of WEP, a seriously high amount of WEP, to 2,100 milligrams per liter, a farm that actually knows that they do not have a phosphorus problem because of that low level. And so what you see here is that you see, though, as we add MDR, all of the WP values are lowered, and particularly if you go out to extreme concentrations, loading rates, loader addition rates, beyond 20 grams per liter, you see that we get consistently the WP greatly decreased at all sites. However, that is not an economical level. The range that we're looking at as being useful is in the 5 to 10 gram per liter addition rate. And so if you use your eyeballs here, and I think if you can see my mouse here, we're looking at an area where we get between 40 and 60% removal of high WEP concentrations. So that's, as I said, that is the area where this could be a cost-effective way to lower the WEP and bring it from a high level, which is environmentally of concern, to a level which is a medium level, which is not as environmentally worrisome. So this is actually then the greenhouse crop yield evaluations that Dr. Stahauer did for us. He did this by growing ryegrass in a greenhouse, and he grew the ryegrass on a nutrient deficient soil, and in particular a nitrogen and a phosphorus deficient soil. And the control pots, which didn't have manure, didn't have any treatment other than the soil, actually grew the lowest quantities of ryegrass. Then manure was added as the nutrient source in these experiments, and so we had some plots that received only manure, and then we had 4 levels of MDR that was added to manure. The concentrations were on the low end, and then we had one concentration that was 32 grams per liter, very, very high end. And the idea here, the question was, does adding MDR to the manure tie up the phosphorus to such a degree that it's no longer available to the plants, and the plants then do not benefit from the phosphorus in the manure? And this is a common question we get from farmers, is this going to hurt my crop yield if I do this? And what we found, and what Dr. Stahauer found in this experiment, is that even at the highest concentration, there was no decrease in ryegrass growth due to MDR addition. And so MDR does bind up the WP phosphorus, but apparently the WP is still available, is still extractable by the plant roots and the plants to be utilized by plants in plant growth. The other thing Dr. Stahauer did is he would periodically run a large amount of water through these pots on purpose and collect the leachate from the bottom. And that then gives an idea of how much, again, another estimate of the water-soluble phosphorus. And what we found was less water-soluble, less phosphorus in the leachate from the MDR-treated pots than we did from the control pots. So again, these were nice greenhouse experiments to verify to us that we're not seeing any crop yield problems, and that this is another independent estimate that the MDR approach really does lock up soluble phosphorus and keep it from leaching from the soils. Okay, so then, for the last couple of years, we've been doing field trials, and this just, their field trials, we've made an effort here to vary things as much as possible. We've ranged from small, 80 cow operations up to a very large, a 3,000 cow milking operation in Center County. And the manure storage has, in all cases, there was manure storage of some kind on the site, and the manure was eventually land applied. And in the case on in the left, the bottom left here, this is a freestall barn. This is our this was about 100 dairy cows that fed in this enclosed area. As you can see, they actually bedded this with the bedding here was sawdust, and then once a day, all the bedding and all the waste were shoveled and washed into a sump that went to a storage pit for eventually be land applied. The middle slide is a picture of a 400,000 gallon in-ground concrete manure storage tank, and you can see that this is very full. This was last April, and this was 2 days before that tank was cleaned out by a manure hauler who came in, pumped all the manure out, and spread it on about 120 acres of local fields. And 2 days before he did that, we actually added MDR to that tank. The material on the right here, this is actually the sawdust bedding that was used by the freestall operation. And their original plan there was to actually hand apply the MDR to the stall, to that large stall, independent of the sawdust. And that became a dusty affair, and it just became a difficult extra step for them in their operation. And so what they ended up doing after some talking with us is they just added the MDR directly to the sawdust, and that's what you're seeing here. And then they applied that. They had no problems the cows, with the milk production. They had no problems with, with cows that they could observe cows lying directly, of course, on the sawdust. And actually, you'll see in a second here that we got very good results from this approach. Okay, and so what we saw in the field trials is we saw water extractable phosphorus was decreased between 22 and 66%. On the lower numbers are because either, on one case, either there wasn't very high water extractable phosphorus to start with, or actually in our last experiment, we started fooling with low dosing rates to see what kind of result we could get. And we actually went down to only 4 grams per liter. And we found, just like our laboratory results showed us, we only got about 30% removal lowering of the water extractable P because our loading was so low. But as we saw on previous slides, and we'll show, I think, in the next slide here, we still got very similar, very good results, very good correlations between what we measured in our bench testing with our lab experiments and what we saw in the field. And really, we saw, we had farmers work with us here in applying the material. And what you can see here in this photo, this is the main problem that we had with dust. This material was dried to about 80% solids and then was finally ground up in that Palva ball mill. And so it has the potential to be dusty. And when the bags that were being cut open and then lowered, then released, the iron oxide, the MDR was released into the tank. When those bags, were held high and cut large, it made a big dust problem. And what the farmers very quickly found was ways to minimize the dust. And I think dust is a issue that can definitely be dealt with just a better application processes. So that was really the only problem that the farmers who worked with us could identify as the only part of the MDR addition that they wanted to work on. Okay, so this actually gets down to, in Pennsylvania, we have something called the P index, and this was developed by USDA and RCS, USDA ARS, working with Penn State faculty and US Extension faculty to determine how to measure the vulnerability of a field to producing environmentally mobile phosphorus. And then once that's a measurement's been made that shows there's a dangerous or an environmentally unsuitable situation, then having a way to show the farmer ways to mitigate for those phosphorus problems. And so what I'm showing here is a typical P index calculation. The P index calculation takes into account the phosphorus content of the soil that you're starting with. It takes into account how much fertilizer you're adding during your cropping on that field this year. It takes into account how much manure you're adding during your cropping this year. And it takes into account how your fields are connected to the receiving streams. And so the baseline is a soil which has 210 parts per million phosphorus, which is a good amount of phosphorus, and it's being cropped, and there's fertilizer being added at 20 pounds of phosphate per acre, and the method is it's being injected. And these are all parameters that you can change in the P index calculation, how the phosphorus fertilizer is applied, how much that goes into the calculation. In our baseline, manure is being added at 90 pounds of phosphate per acre, and that's about 5,000 gallons of manure per acre. And it's being applied on the surface, and in our baseline, anytime, no rules on when it happens. The P source coefficient, which is a measure of the WEP, is 0.65. That number can range from 0.1 to 1. That is the range of that number. As you get closer to 1, it becomes a more serious problem, because that means there's a higher proportion of soluble phosphorus in your manure. 0.65 is a higher level. It's not 0.8, which is the default value in these calculations, but this was a value that we saw typically in small dairy farm operations where stored manure was being spread on the fields without any kind of solids management. This is probably a typical value from our study. And then the transport part is there's erosion, which we didn't fool with that. That's a standard in these calculations. But here, the transport part was how close is the manure to, how close are the fields to the stream? And so what you see here is then moving to the right here is the ways that you can decrease the P-index is you can change the buffer. You can increase your buffer. You can move your fields. You can set up an extra 100 feet of buffer, and that decreases your P-index to 86, which may allow now the use of that field, whereas before you couldn't. You can then also, the standard way is to work on your manure management process. You can decrease the amount of manure you're adding. You can cut it in half. You can cut it to 2,500 gallons per acre, and that has an effect of decreasing the P-index to 75. You can modify when you spread the manure. Instead of spreading it anytime, you can be restricted to only spreading it in times when runoff is least likely to occur. And so that would be, that can affect the score. And what we have here is a new column, it's our new column, is you also could do something to decrease the P-source coefficient of the manure. And what we see here is a 5 to 10 gram per liter addition would decrease that value to about 0.3. And here you can see that really that change has the same effect as decreasing the manure application rate by 50%. So with farmers who particularly don't have the ability to decrease their manure application rates without transporting it large, expensive distances, this is a good short-term solution for them to pass the P-index calculations, possibly very cost effectively. Okay, so summary to date, then whenever we're working, what's come out of this phase 2 of the work is that we understand the importance of screening any MDR or any solid material. One result for use in agricultural and manure treatment applications, I think one result of this research may be that lots of people with solids are going to think, well, gee whiz, maybe my material can affect WEP and want to get it evaluated as a potential material for WEP control. And it's going to be very important if that happens that there's a rigorous screening process first. The second thing we see is that chemistry is important. We didn't go into that in a lot of detail, but the MDRs with the highest metal contents, iron and aluminum in particular, were the best performing MDRs. And so chemistry is important, but particle size is also very important. And so the materials, if the materials are coarse grained, they're not going to be as effective as fine grained. So that's an important parameter. And we saw that in our applications, dust was the main problem that the farmers had. And we see no evidence that MDR interferes with plant growth. And a very important unexpected thing that we found here is that not all manure needs phosphorus management practices. And so that's an important part, is making sure the manure needs phosphorus reduction, WP reduction, before you go into treating it with any kind of MDR or similar material. So our next steps, this webinar is going to conclude the phase 2 of this project. We're going to move right away into phase 3. We have the lab, the Penn State lab is going to develop a standardized method for evaluating solids, like our MDRs and other solids, for use in this application. That will involve a standard method for measuring the hazardous metal content, and also a standard method for actually doing the dose effect experiments testing that we developed here, but the Penn State lab is going to develop a standard method so that anybody could send to the lab a solid material, an MDR material, and a manure sample, and they'll be able to tell you what the dose effect relationship is, and they'll also be able to tell you whether that material is suitable for application to manure in a farming environment. The fact that the USDA, the ARS folks, they're going to do some simulated precipitation experiments that compare the runoff of phosphorus in controlled field experiments from MDR treated manures and non-MDR treated manures. We hope that this will lock down the benefit of adding MDR to manures and actually decreasing the transport of phosphorus off of farm fields. We're going to do more dose effect testing and field trials, but we're going to increase it. we're going to move into swine manure. In phase 1, we did some swine manure testing, and we got very good results. Phase 2 was focused entirely on dairy manure, but we're going to move back and start looking at swine manure because that is an increasing problem in Pennsylvania. We're going to do more field trials, and we're actually we're going to do crop yield measurements on a field basis. We have Team Ag, a large local agricultural consulting firm in Lancaster. They're going to be actually measuring crop yields in fields as in association with our trials, crop fields treated with MDR and fields not. And lastly, we're hoping that all of this can work its way into a best management practice. And that's where we're going is towards getting NRCS and the Pennsylvania State Conservation Commission to recognize this as a legitimate approach and as a best management practice that then farmers and nutrient management specialists will have in their toolbox.
And so this is Amy again, and that really wraps up our webinar. And before we open it up to take questions, I do want to mention that moving forward with this phase 3, we are looking for farmers that have phosphorus problems. So those of you listening on the webinar, if you know of any farmers, or if you know of other nutrient management specialists, other folks who may work with conservation districts who would have knowledge of these farmers, we would like to reach out to these farmers and potentially work with them with our field trials. We do have some reimbursement available for the farmers' time that we would be able to pay them for. And we are looking for project locations in the Chesapeake Bay. As most of you know, it is a priority for the Pennsylvania DEP. So that would be our first target area. However, we're not limited to working just within the Chesapeake Bay. And so at this time, we'd like to open it up to questions. I also want to mention here that this, let's see, I can't bring, there we go. So I wanted to also let you know that once we're done with this webinar, we will make it available later on at this website here, and I will be sending an email out with this location where you can find the recorded webinar, so it can be viewed at any time, and please pass this along to anybody else who you think might be interested in viewing this. So thank you for listening to our webinar, and can we take questions now?
I think we can. If anybody does want to talk, we're going to unmute